It's not really fair to put me on after all these guys, is it? But I'll see. Anyway, you've seen these images before. This is the Earth seen from space, the surface ocean. As Manu explained to us, we can interpret the reflected light spectrum to understand where and when chlorophyll is abundant in the surface ocean. So in these green and yellow and red spots, there's an intense concentrations of chlorophyll, and that means that the organisms are absorbing dissolved carbon dioxide from the water, along with other nutrients, building organic molecules, and some fraction of those organic particles ends up feeding the fish that we and other animals eat, after passing through a food chain involving many of these beautiful organisms that we see around us. Another fraction of it ends up sinking into the deep ocean and storing carbon there, taking carbon out of the atmosphere and so affecting climate. And so it's a tremendously important process. And as given our concern today over the role of the carbon cycle in modulating climate, we're interested to try and understand how these effects may have affected past climate or be related to past climate changes and respond to ongoing climate change. And to do that, one tool that we try and use is computer simulations. So the analogy is the weather forecast model. Every night on the TV you could watch a news weather forecast and see visualizations of the forecast of tomorrow's weather. You can go outside tomorrow and it may or may not be the weather that was predicted. And we can try and build similar tools to simulate what's going on in the ocean, the plankton and the carbon cycle, to think about and ultimately hope to predict how the near or far future carbon cycle might be changing, and think about how we can respond to that or try and modify that in advance. It's quite difficult because the plankton, as you've already been hearing, while all the plankton have chlorophyll in them, this doesn't work right. They're not all the same, and they're doing many different functions. So this beautiful diatom here, we just saw some of those for a Coscinodiscus from out of the harbour, just sampled last night. There's a beautiful one up here, I think. They have a mineral structure that makes them sink when they die and bring that organic carbon into depth. The beautiful colony in the background is a trichodesmium. It fixes nitrogen. It takes dissolved nitrogen gas as its source of nitrogen instead of using nitrate or ammonium that most of the other plankton are using. And so we not only want to understand how the chlorophyll and the bulk carbon phytoplankton community is changing, but we also want to understand the details of how the different types are changing. And that's it becomes a much more challenging task in many ways, not least in understanding, just from an observational point of view, how the distribution of these different organisms looks today in the global ocean. So I'm going to try and give you a brief look at how we might build computer models to kind of sim worlds, if you will, to explore this system and hopefully gain predictive power. We're not really there yet, I think, in terms of the latter, but we're on the way. And I want to go back to the 1940s to a really pioneering scientist, Gordon Riley. And he and a team of colleagues in the late 30s and early 40s would visit George's Bank. It's a fishing ground here off the coast of Massachusetts. So here's Boston, where I live. Here's a fishing ground at George's Bank. And these are images of the chlorophyll concentration from space. And during the spring, it was already known then, of course they didn't have these satellites at that time, it was already known that there was a strong seasonal variation. And Riley and his team went out to sea and did a really groundbreaking set of measurements. And here's how they visualized this seasonal variation. They're looking at the concentration of phytoplankton, we call it B here, as a function of month, so January, February, March through to December. And they had a few cruises and observed the system several times during the year, and you can see this increase in chlorophyll in plankton concentration during the spring, very classic for these temperate waters. And you probably see the same thing in the opposite seasons around here. And so Riley was interested in trying to build a mathematical model to predict how the chlorophyll concentration would vary with the seasons, with the environmental changes that happened in the seasons. And he wrote down a very beautiful equation. I don't want to worry you if, like many of us, you haven't done much math since a long time ago. But I just want to give you the flavor of how this works. This is a very general principle. So he wrote down this beautiful equation, which even 60, 70 years later is basically the same way that many of us would still represent this system mathematically. And it says that the rate of change of the phytoplankton concentration, so how steeply this curve rises and falls, depends on the balance between growth processes and loss processes. So this is population growth, and it depends on the availability of nutrients. It's like your plants, you feed them, they grow. And death processes. If there's lots of creatures around that would like to eat them, then they will reduce the population. And so if growth is faster than loss, the population grows, and vice versa. And you can write that down mathematically, and you can solve that equation to predict how the population will relate to the environment that controls growth and loss. And Riley did exactly that. It was really amazing. He had no computer. It took him a week to solve these equations to produce this white curve, which actually is a rather good fit to those blue data points that were the observations. It passes close to many of them. And this was a tremendously powerful tool. He could then infer lots of things about the system that he couldn't directly observe by combining the maths and the data together. Together, the two things are more powerful than either one alone. Again, this is very important because it's the way we still do things, but we now have big computers and we can solve more complex equations or many more equations. I'm going to now kind of flip to today and think about kind of sim worlds, if you like, these virtual worlds we can use to try and simulate the ocean system. And again, there are analogies of the weather forecast models. So when you look at this is again George's Bank. It's now virtual George's Bank. So here's George's Bank. Here's virtual Massachusetts. It's like a computer game, so it looks a bit blocky. We've divided the world up into 20 by 20 kilometer squares. And in each of those squares, we have a series of equations to describe the changes in temperature, salt, plankton concentration, nutrient concentration, and we solve them in time, but we can do it much more quicker than Riley could. So instead of taking a week to solve one equation at one point, we can, in a few seconds, solve tens of equations at millions of points and make a prediction about the global system. And so how am I doing? Whoa, 3 minutes. So, good, I'm good, yeah. Thank you. So as you see, as we zoom out, we can't see the little squares anymore, but we can see a simulation of the global ocean. This is the surface temperature of the global ocean. You can see these beautiful eddies in various places. You can see the warm oceans in the tropics and the cold oceans in the poles. That's just done by simply solving a set of equations at each of those points that talk about the sources and sinks of temperature. We can add additional equations. We can solve for the flow. So as your weather forecast model will tell you about the winds, the ocean model tells you about the speed of the currents. And so the white areas indicate where we've got swift currents, like the Gulf Stream here. These beautiful eddies the Agulhas rings in the southern Atlantic that the Turret expedition looked at the plankton populations in these features, and there's lots of beautiful features. And ultimately, we've also made a prediction about the population of the phytoplankton. And so remember, what we've done here is that in millions of grid points, we've solved an equation, basically the one that Riley wrote down, and we can do it very efficiently because we have the computational tools. Perfect. So, if we look at the top panel now, we can see that prediction of the chlorophyll distribution. And we, just as you can go outside tomorrow and decide for yourself whether the weather forecast was accurate or not, we can use the satellite data that Emmanuel showed us and decide whether the simulation of chlorophyll was accurate or not. The model is also predicting the populations of the different plankton types. So all of them have chlorophyll, so we can look at the total chlorophyll, but we can also make a prediction about the contributions from different plankton types, including, for example, where you can see bluish colors. These are these nitrogen-fixing organisms. I showed you that beautiful tufty nitrogen-fixing trichodesmium before. The problem with this panel is we actually have not as much data as we would like to test this, so we don't know if this is really right or wrong to some degree. We can say some things about that, but we're really data limited because it's hard to go out in the ocean and collect the data that can tell us about these distributions. It's hard to extract those distributions from the satellites at this point in time. I'm almost there. So if we just look at one of the types, the nitrogen fixer, this red distribution tells us where we predict that it will be in the global ocean. The little white dots indicate a compilation from a few years ago of where genetic data samples in the ocean have said there were high concentrations of these types of organisms. There are quite a bit more data nowadays. For example, Tara fills in a few spaces on this map, but there's still very large regions where we simply don't have any data. The model says there isn't any nitrogen fixation here. We don't know if there is or isn't. And this is where citizen science, where Plankton Planet can really provide a huge boon to this whole effort to develop predictive models by efficiently increasing the number of dots on this graph hugely at a relatively low expense relative to traditional ways of sampling the ocean, and through the cooperation of scientists and citizen sailors who are interested in helping us characterize the planet. And so this is something I think we really look forward to. And I'm hoping that within the next years and decades, through this cooperation, we can understand and improve these models and ultimately use them to help decide how we should alter our own treatment of the planet or not in order to preserve or modify the functioning of the plankton populations, the carbon cycle. Thank you.